A black hole is the most extreme object in the universe. If you fell into one, you would experience forces unlike anything else in nature. This is what would happen to you, step by step. Black holes form when massive stars collapse at the end of their lives. The star's core compresses into a point of infinite density, called a singularity. Around this singularity is the event horizon, the boundary beyond which nothing can escape. The event horizon is not a physical surface. It is the point where the escape velocity exceeds the speed of light. Once you cross it, you cannot turn back. As you approach a black hole from a distance, you would notice its gravitational pull increasing. Space and time around a black hole are warped by its mass. Clocks near a black hole run slower compared to clocks far away. If you were falling toward a black hole feet first, gravitational forces would begin to stretch your body. This process is called spaghettification. The gravity at your feet would be much stronger than the gravity at your head. For a small black hole, spaghettification would begin outside the event horizon. Your body would be stretched into a thin strand before you even crossed the boundary. For a supermassive black hole, you could cross the event horizon intact. Supermassive black holes are millions or billions of times the mass of the Sun. They exist at the centers of most galaxies, including our own. The event horizon of a supermassive black hole can be millions of kilometers across. If you fell into a supermassive black hole, you might not feel anything unusual as you crossed the event horizon. The tidal forces would be weak enough that your body would remain intact. You would pass through the boundary without any clear signal that you had done so. However, someone watching you from a safe distance would see something different. As you approached the event horizon, you would appear to slow down. Light from your body would become redshifted and dimmer. From the outside observer's perspective, you would never quite reach the event horizon. You would appear frozen in time, fading from view as the light stretched into longer and longer wavelengths. This is an effect of time dilation near the black hole. But from your own perspective, you would cross the event horizon in a finite amount of time. Once inside, all paths lead toward the singularity. The singularity is no longer a place in space, but a moment in your future. Inside the event horizon, the roles of space and time reverse. Moving toward the singularity becomes as inevitable as moving forward in time. You cannot stop or turn around. As you fall deeper inside, tidal forces would grow stronger. Even in a supermassive black hole, spaghettification would eventually occur. The difference in gravitational pull between your head and feet would increase. Your body would be stretched vertically and compressed horizontally. Atoms would be pulled apart. Eventually, even subatomic particles would be torn apart by the tidal forces. At the singularity, density becomes infinite, and the laws of physics as we know them break down. General relativity predicts the singularity, but it cannot describe what happens there. A complete theory of quantum gravity would be needed. No information can escape from inside a black hole. This creates a paradox known as the black hole information paradox. Quantum mechanics says information cannot be destroyed, but black holes appear to destroy it. Some physicists believe information is preserved on the event horizon. Others propose that it is released through Hawking radiation when the black hole eventually evaporates. This question remains unresolved. Black holes slowly lose mass through Hawking radiation. This is a quantum effect at the event horizon. Virtual particle pairs form near the boundary, and one particle escapes while the other falls in. For stellar mass black holes, Hawking radiation is extremely weak. A black hole with the mass of the Sun would take longer than the current age of the universe to evaporate. Supermassive black holes would take even longer. If a black hole is small enough, Hawking radiation becomes significant. A black hole with the mass of a mountain would evaporate in a fraction of a second. As it shrinks, it radiates faster and eventually explodes. No human could survive entering a black hole. The tidal forces would destroy any material object long before reaching the singularity. Even spacecraft made of the strongest materials would be torn apart. Some theories suggest that rotating black holes might contain stable paths that avoid the singularity. These are called closed time-like curves. However, these solutions may not exist in physical black holes. Other theories propose that black holes could be connected to white holes or other regions of spacetime through wormholes. These ideas are speculative and have not been confirmed by observation. The closest black hole to Earth is Gaia BH1, located about 1,600 light-years away. It poses no danger to our planet. Black holes do not roam through space, consuming everything in their path. A black hole only affects objects that come very close to it. At a distance, its gravitational pull is the same as any other object with the same mass. If the Sun were replaced by a black hole of equal mass, Earth's orbit would not change. Scientists study black holes using X-ray telescopes and gravitational wave detectors. Matter falling into a black hole heats up and emits X-rays before crossing the event horizon. Merging black holes create ripples in space-time that can be detected on Earth. In 2019, astronomers captured the first image of a black hole's event horizon. Entering a black hole represents a one-way journey to a place where physics, as we understand it, ceases to function. The extreme environment would destroy anything that crosses the event horizon. What happens at the singularity remains one of the deepest mysteries in science.